In this video, we're going to solve equations using logarithms. So I've written an equation already. I've got 2 to the x equals 12. Okay, and so when you first encounter this, your first instinct might be to say, well, 12 divided by 2 is 6, so x is 6. But that's not true, right? This is not 2 times x. This is 2 times itself some number of times until we get to 12. And we know that that's not going to be some whole number, right? We're going to get a decimal for this. So we have to have a way to solve this with x in the exponent. So if we think about what this is really asking, this is saying what power of 2 makes 12? What power of 2 makes 12? Well, that sounds kind of familiar. If you've watched another one of my logarithm videos, you know that logarithms ask what power of a number. So what this is really saying is what power of 2 makes 12? This is another way of writing what power of 2 makes 12. That's what logarithms do for us. So what power of 2 makes 12? That's going to give me my answer. Okay, and once you get it into this format, we've learned that there's a couple different ways to solve this. If you have a graphing calculator, you can just type it straight in. If you don't, or you just like doing it with the change of base formula, you can convert this thing to log of 12 over log of the old base 2, like this. And that's going to give you the same answer. So this guy you can just type in the calculator pretty easily. Log of 12 divided by log of 2. And I already did that. And so x is 3.585. And that's rounded off, right? This is a decimal that doesn't terminate. So I had to round it to the third place. So I just picked that randomly. But there we go. We've got our answer. What power of 2 makes 12? 2 to the 3.585, blah, 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 makes 12. Okay? Cool. We can also put expressions in the exponent as well. So we could have something that looks like, say, 5 to the 2x equals 10. So 5 to the 2x power equals 10. So this is, again, this is saying what power of 5 makes 10. What power of 5 makes 10? We have some extra stuff to do at the end once we figure that out because we have a 2x in the exponent, but we're still just trying to figure this out. Okay, and so that's a logarithm. Log s what power? What power of 5 makes 10? Well, that's going to be whatever that exponent is. That's going to be 2x. All right, so what power of 5 makes 10? That's going to be what my exponent of 2x equals. So you calculate this, right? So you can do change of base formula. You can plug it in. I'll write it down as the change of base formula problem just to get some extra practice in for that. So we can turn that into log of 10 over log of 5, just with common logs, equals 2x. You can type this into the calculator. That's going to give you a decimal. You're going to get about 1.431 for that. And I rounded that off. It's, in best practice, you should leave the whole decimal in your calculator at this step, and then divide by 2. Let's see what x is. So x is 0.715. Okay, so x is 0.715. So that means if I go back up to this original equation and do 5 to the power of 2 times 0.715, I'm going to get about 10. Okay, so that's one way of thinking about these problems, is to sort of turn them into log form. There's another way to do these problems that will get you the same answer. In fact, I'll just go ahead and do the same problems again, but in this new way, okay? So this is going to use the properties of logarithms that we talked about. So let's go back to that first one that we looked at. So we had 2 to the x equals 12. Okay? So again, remember, if we're going to solve this thing, we have to get this x out of the exponent. And another way to do that is using our power property of logarithms. Okay? And so this one's kind of nice, because all I need to do is turn these into a logarithm somehow, and I'll be able to pull that x off the exponent. The good thing about this is it makes no difference what kind of log I use. If I write the log of 2x equals the log of 12, that is still a valid equation. That means the same thing as our original equation. You can put a log in front of both sides of an equation. That's okay. And now that I have it in logarithms, we have that property where you can take that x from the 2 and put it right down the front. So that can become x times log 2 equals log 12. And so now log 2, this is just a number. Okay, you can type this in the calculator, it's going to give you something, right? So I can divide by that number and divide it off of x and figure out what x is. And then, of course, just like solving any other equation, you've got to do it to both sides. So log 12 divided by log 2. just common logs in the calculator. So when you do that, you'll notice it's the same thing we had in the last problem. We had log 12 divided by log 2 at the last step there before we calculated that thing, and so it's 3.585 again. So it's just another way of thinking about it. Maybe you like converting it into log form. Maybe you like doing it this way. I kind of like this way better because it really doesn't, I don't have to think about what kind of log I'm using. I just use a common log, okay? Let's see how that works with a couple other example problems. Let me get some more complicated problems out here for you. Let's take a look at number 9 on this worksheet together. Okay, so number 9, we got 5 times 18 to the 6x power equals 26. And we want to solve for what value of x can I put in there to make this thing true? What value of x is going to make all this stuff equal 26? And so since x is in the exponent, I know I'm going to have to use a log somewhere in there to solve this thing, okay? Now, we can't start using logs or any of those tricks until this exponential piece is all by itself, right? It can't have this 5 in the front. So we just kind of go back to our normal algebra canceling stuff, and we can cancel that with division. So I can divide 5 by 5, and I can divide 26 by 5. And so that's going to give me 18 to the 6x equals 5.2. Okay, and so now it looks kind of like some of the other examples we already looked at. So I'm going to use the second technique where I just take the log of both sides. Like, I don't even care what kind of log it is. It could just be a common log. I'm going to write log of 18 to the 6x equals log of 5.2. And then that sets me up to use my properties of logs where I can take this whole 6x and just bring it down, plop it down right in the front. And so we get 6x times log 18 equals log of 5.2. Okay, now I'm kind of running out of room here. So let me just kind of, I'll scribble that out. Let's keep on going here. Okay, so again, we're solving for x. And right now, what I have is 6 times x times the log of 18. So I have a bunch of multiplication here. So I can divide by 6 to cancel this guy out. Okay? And so I get log x times log of 18 equals log of 5.2 divided by x. Divided by 6, excuse me. And so then, again, I have this log 18. That's just a number, and I can divide by that as well. So I can divide by log 18. And so that's just going to pop a little log 18 down here in the bottom with the 6 that was there. So I can sort of think about dividing 6 and log 18 in the same step if you want to. You can just put 6 times log 18 down here in the bottom. The point is, everything's gone over here. I just have an x, and this stuff is just a number. Right? It's just, I can type all this into a calculator. It's going to spit a number out for me. And so when I type that in the calculator, that spits out 0.0951. Okay, and so there's my answer, 0.0951. If I come back up to this original problem and do 5 times 18 to the 6 times 0.0951, that's going to give me 26, okay? Let's run through one more. Let's take a look at 19. Let's do just like a super crazy one here, just to make sure that we can do it, okay? But we're just gonna follow the steps, right? We don't have to worry about what's in the problem. We just take it a step at a time. That's the nice thing about math, is we can trust the process, right? So for this, to be able to solve this, I have to get this exponential piece by itself. I gotta look for some stuff that's not a part of that. And so I have this plus, or this minus 1, so we can just get rid of that guy by adding 1 to both sides. Okay. So then we get negative e to the negative 3.9 n minus 1 power. Okay, kind of a crazy exponent there. And that's going to equal negative 2 now. Okay, now I've got this negative e and I got this negative 2. Okay, so I can just make them both positive, plus plus. All right, just change the signs. And we get e to the negative 3.9 n minus 1 power equals positive 2. And now I have this exponential piece all by itself. I can start to think about what logs to use. Now, when you see e, you know we're not dealing with common logs anymore. We're dealing with natural logs. Okay, so what we can do is take the natural log of both of these sides. Okay, so we can do the natural log of e to this crazy exponent equals the natural log of 2. Okay, now I can do the same property of exponents that I always do. So I'm going to take this exponent and I'm going to drop it down in front of this stuff. Okay, so I'm going to come up here and sort of write it over here now. So this exponent is dropping to the front of the natural log. So I'm going to get negative 3.9 n minus 1 times, that's a times sign, natural log of e, equals, this stuff on the side is still natural log of 2. Okay, now, the nice thing about natural logs and e is they go together, right? This ln means we're talking about a log of a base of e. And so this is asking, what power of e makes e? What power of e makes e? Well, e to the first power. So this thing is just a fancy way of writing the number 1, okay? And since we're multiplying by 1, it doesn't change any of this stuff. So really, it's kind of like it cancels out, and we just get negative 3.9n minus 1 equals the natural log of 2. And then this is just back to a 2-step algebra 1 equation. Looks complicated because we have this natural log in there, but it's not. We just add 1 to both sides, okay? And then, so we get ln 2 plus 1, and then whatever that is, we take that and divide it by negative 3.9 to cancel it off. So divide that by negative 3.9. My notation's kind of sloppy, but that's not the point. The point is the math, okay? And so all this stuff's gone. We got the n, and then you're just going to do this in the calculator. Natural log of 2 plus 1, get your answer, divided by negative 3.9. And when you do that, you get negative 0.4341. So it's okay. We get these crazy decimals for these. A lot of times it feels wrong to get a decimal for some reason, but no, these give you some crazy answers. Okay, so what this means is that if I replace this in the original problem with this crazy decimal, all this stuff on the left is just going to become negative 3. And so we've solved it.